That's the way I do. And it's nothing, this is all covered yesterday. So this case, when it goes straight up, then you can tell this is for surface ship, right? If you have a slope to goes up, that's really for submarine. And whenever it goes straight out there, that's really nuclear explosions. So you can tell right away. I can tell this is a surface ship, and this is a submarine, and this is submarine, right? You can tell. It's a conventional, it just decelerate. This is, remember, acceleration versus time. So it decelerate, okay? This rate of deceleration may change, depend on the depth of the target. When I say target, Hassan, how you feel? It's good? Okay. Yeah, it's fluids going around. Yonok was sick. I was kind of sick. It's a flu. Be careful. Willis had a flu, no? No. So this is bodily response, means again velocity of a whole target as one unit, as a rigid body. It kicks, right? So that's what that is. So to look at the shipboard equipments, then that is the excitation apply to the base of shipboard equipments, okay? So that's what you should consider. Then it's very easy. And we're gonna talk, you don't have such a, my comment in your note, right? Do you or you don't? You don't? You have such a comments in your note? No. Okay. Anyway, this is another version, but doesn't make any difference. We thought it would be better. I usually give, when I teach the vibration class, I give a quiz. Quiz means a smaller size of the test or exam. Derive the equations of motion for this. This is like shipboard equipments. Shipboard equipments include even turbine. The whole turbine, including turbine pedestal, turbine itself, or some people think a large, what's this noise? The large pump sitting on the foundations. That foundation is also sitting on the deck, for example. So simplest model is exactly that. So this is mass M. Simplest model. And then you have the stiffener. This stiffener is a support system. This is the simplest model. Then I said, okay, the base is in excitation. I usually use Z coordinate, Z. Base excitations, okay? And I gave the motion, this is motion, this is, let's say, X. In this system, how many degree of freedom does it have? Some stupid question, but anyway. How many degree or degrees of freedom? 2 coordinate. How many degrees of freedom? Jongwon. Single degree of freedom. So as I look at Jongwon's eyes, Hey, professor, what are you talking about? This is a single. Why? Well, direction of motion is up and down, right? And this doesn't matter. The mass is the matter. Okay? The motion of mass m allowed to move is in vertical direction. So mass has only one direction, that particular degree of freedom. So this is a very simple single degree of freedom system by the base excitation. Then, as I wrote down there, so now develop equations of motion. It's just Newton's second law would be the choice, right? So, the way I suggested to develop the equations of motions, very straightforward, then you will not screw up. That's the way. Sometimes this base motion, when I introduce a base motion, it's very, people can easily make mistake based on my experience for many years. So, here I'm going to say x minus y is x minus g. What do you call the y? Relative displacement, isn't it? So relative displacement, if then I'll just draw the free body diagram. So if I give, when you have a base motion, this guy will have also the motion, and this direction, upward direction, is a positive x direction. Okay, if I excite this guy a little bit longer than the z, then spring will be stretched, right? If a spring is a stretch, if I cut it, then what happens? Which is same as applying the force in downward direction, right? So the relative displacement that the spring experience is y, right? In downward direction. So you have like a spring constant times y, which is really k x minus z, right? And I always put the inertial force in the direction you apply the positive x direction, which means inertial force is mass times simply x double dot. Done. So then mx double dot is equal, that's important, Newton's second law. Then is it k x minus g? Is it plus or minus? Minus, right? Because it's in opposite direction, so I'm going to put the negative sign here. That's all. Then the m x double dot. So if you open this guy, plus kx is equal to plus kg. That's one way. Another way is if I'm going to reset this guy as a y, right? So if you reset that guy as a y, then what happened? So this is here, y is equal to x minus g, right? Is equal to x minus g. Then y double dot is equal to x double dot minus g double dot. I can rewrite this guy down here as x double dot is equal to y double dot plus G double dot and plus KY is equal to 0. So if you do that, MY double dot plus KY is equal to minus MZ double dot. So this is one form. This is excitation, you know. Only unknown is a Y here. So that's very easy to solve. And if you divide everything by M, K, Y is equal to minus G double dot. So here K over M, what is it? What do you call that? Natural frequency. Usually called the natural circular frequency because this guy is omega n squared. Okay, omega n is radian per second, right? So omega n is square root. This you will never forget, right? Whether you learn the acoustics, underwater acoustics, vibrations, shocks. So this is radian per second. And what's the relation between omega and Fn? Just keep reminding, same thing over and over again. 2 pi Fn is equal to omega n. Right? So Fn is what? Cycle per second. Or you call this guy as a hertz. So that's what this is about all for base excitation. For single degrees of freedom, if you understood, I know you will understand 100%, then multiple degrees of freedom or cast into the matrix, exactly identical approach, very straightforward and simple. Okay? So that's what I'm doing here. But one thing is when you have my double dot plus ky, of course this is all time domain function, minus, I use m small m, or in my note capital M is the same, by the way, here. I start to write lowercase m, so uppercase or lowercase is the same thing. Okay? So if as I look at this, you know, when the base is in motion, not comfortable. You know, in California, earthquake is kind of very popular. In 1989, we have a 7.6, the Richter scale earthquake. It's really bad. And that time my children were small, and there is no place to hide if base is in motion. Base is in motion, where are you going to hide? So total frustration when earthquake occurs. I was sitting there that time in my office. We had a faculty meeting done about 15 after 5 p.m. in the late afternoon. Then bang! Whenever earthquake occurs, some explosive sound is coming. Then it was a concrete, precast concrete, the building. Then I was almost sitting on a chair and bang, I almost flipped in the back. And I look up the beams, concrete beam. I can see it, the whole beam is moving. So scared. But earthquake, you have a time to think. Shock, you don't have a time to think. So that's a big difference. So time to think means earthquake, you have a time to feel the damping is in place and working. Shock, you don't have a time to feel damping. Damp, energy is really dissolved. You don't have such fields in there. Then bang! Then I see it. I couldn't move. I totally froze because it's moving. You know, it's a finite displacement. Shock, bang! You don't feel the displacement, but you feel the acceleration. You feel the force. Then I look it up. My body was totally frozen up. Then about 10 seconds after, I feel, oh, this is earthquake. Then start to place to hide. Then in the office, where do you go? Crawl under the table. Under the table. Then it stopped after another 20 seconds. 20 seconds is like 1,000 years. Yeah. Then it stops. Then I stand up, get up, then open the door and ran outside. It's but Korea has no earthquake, but I heard we had some minor earthquake activity. That's what I heard. So when the base is in motion, not good. So now you can convert the same equation. This is equation, or this is coming from the equation mx double dot plus ky. Same equation, okay? So if I recast this equation into the model, what I can do is, this is my double dot, so this guy is a y. And now ky, this is k. There is z double dot, this guy is what? This is input, right? Z double dot. It's a derivative, time derivative of the base velocity. So this is base acceleration. So I can tell, okay, I have that force is a negative. So I can say, which is same as applying the force as a minus mz double dot. So base is a fixed. We can convert this into this by looking at the equations of motion. Okay, this is all for the basic equation of motion for the shipboard equipment analysis and design. Okay, identical. Natural frequency is the square root of k over m. And this is very simple. Sometimes you're not going to make mistake, but so this means is Fn is equal to omega n divided by 2 pi. Convert into the cycle per second. Frequency, what's the relation between the frequency and the period? If you know natural frequency, you can compute the period, one complete cycle. So period is equal to 1 over Fn, right? Fn is cycle per second, inverse it. Second per cycle. That's a period. Okay, so this is what this is. Then base excitation, this guy, is in the form that I discussed the day before yesterday and today. This base motion is like a kickoff velocity Z dot, or you start from 0, I could say this, which means reference 0 is the time the shock wave hit the target. Right? Or you can have this guy into this, or this, or you can have all different. If I have this, you can offset, move back to 0 here, vice versa. Or in general, okay, well here, that's okay, step function. Or other function, well, you know, for base excitation, I have this, that's okay. So numerical integration, you can break it down into many steps, and you can just go through numerical calculations. Numerical integration, you can do 2-point integration scheme, or 3-point integration scheme, 4-point integration scheme, all different approach. And I recommend you to take the course, maybe some of you took the course in undergraduate, numerical analysis, all different kind of the approach for integrations and all that. You took it. I'm pretty sure some of you took it already. But like a MATLAB, very typical program, the college students are always using it. It has all different subroutines already programmed, pre-programmed, then you can pick it up and use it. Yeah. Any questions? Very straightforward. Yeah. And what I do, then what I do here is basic model. So I said this is shipboard equipment. This spring is support structure. When you say structure, then you can convert into the spring stiffness of the system. And this is a base excitation. Simplest model. This base excitation, I'm talking since yesterday, like a triangular pulse. This is time. This is Z dot. This triangular pulse is like approximation of actually the measured. Actually, this measured the data. That's approximation. If I do the approximation for this measured data, then as you look through the frequency content in the base excitation, all the high frequency drops off, right? Because all this small fluctuation drops off, right? So when you draw so-called shock spectra, which I will discuss it, shock spectra, then all the high frequency portion is dropped. Because you approximate as a straight line approximation, which may be sufficient for equipment design. Why? Equipment is not sensitive to high frequency. When I say high frequency for equipment level, you're talking about, you can ignore the above 50 hertz. Important frequency is much, much lower. Maybe 20 hertz maybe 10 hertz, maybe highest, maybe 30 hertz. What does it mean, important? The natural frequency, which can resonate with excitation frequency, is in the range of about 20 to 30 hertz, sometimes below, okay? So you don't have to much worry about the above 50 hertz range for equipment design, always low. So usually when you go out to conferences, a lot of time the equipment builder are all coming out to show so-called shock spectra, saying that, okay, this is a shock spectra, is a frequency versus the response. Response could be acceleration mostly, okay? Then they show, this is our design spectra. Which means when they conduct all the tests there, then they draw this design spectra saying that our equipment can resist up to that much, let's say, acceleration. Well, this is like x double that. Absolute acceleration. Our equipments, we guarantee that our equipment can resist perfectly healthy and sound up to that much acceleration between the what frequency and what frequency. So then with that information, you have to design the support systems. You know all the reasonings and all that. That design, you can use so-called DDAM. This is one of the approach that U.S. Navy has been using for many years. Of course, they have a classified version and unclassified version. I'm doing here is, of course, unclassified version that Korean Navy also used before and using it right now. So I'm going to apply general triangular pulse z dot, that kind of the shape. Okay? If I can get the solution response of those kind of the base excitation, then if I do that, then that belongs to this shape, type. Or if I move this time point, let's say capital T, way out there, then that approach to this type wave shape. Or if I reduce this T1, very small, approach to 0, is gonna go into that shape. And move this T way out, T1 way to the left, is going to approach that step function. So what I'm going to show you here is I'm going to show you closed form solution for response of this guy over y, which is x minus g, based on the triangular the velocity, like this. If I do this pulse shape, I'm gonna say up to here, z slope is, I'm gonna say z1 double dot. Why? This is slope is a constant, right? Slope means in this case is acceleration, right? So yes, right? and positive Z1 double dot. And this region is deceleration region. I'm going to say that's a Z2 double dot. The region 1. This is region 2. Decelerate. Acceleration is reduced. Acceleration is, well, velocity is decreasing. Velocity is increasing. Time rate change of the velocity is acceleration. Z1 double dot, Z2 double dot is negative. Then you can solve the problem. Very simple. So then you can deal with a special case. That's what I'm doing here. Okay? Okay. So by looking at this, this is all clear. Very clear, isn't it? Gusto. Clear? Should be very, very clear. And this equation set is all clear. Now get the solution. You have to get the solution of equation of motion, solution of equations of motion. When you solve this the second order differential equation, you still have to be very careful. You know, I taught all different class, something like over the 30-year span. Then I know exactly what the students has in mind in their heart. So I know where, if they make mistake, where they could make mistake. I put that trap in the exam. Mostly they didn't fall into the trap, but still some fall into the trap. So I'm pretty sure this class will not fall into the trap. Because usually when you go run, they have a trap. Then they cover up. Go right in there. But don't go in there. So this is suffering comes along. Okay. So you have, I wrote this a few times. Then you could remember, oh, this? Okay, wrote. Oh, second time, Yangshin, put again. Okay. Third time, put again. So I fed up. Stop. I'm not going to bother to write. Then you remember. So I double dot, time domain function, plus, this is m, k, y. This is minus m, z, double dot. Of course, this is time domain function, general. But in this case, if you use a triangular pulse, then what happens? Z double dot is a constant, right? That's the constant, right? That's simpler. And if I divide everything by m, you have y double dot plus omega n square y is equal to minus g double dot. You have to get the solution for this second order differential equations. And you have, let's say you have a solution. This is solution y. It has a two part. One is what do you call? Homogeneous solution. Another one is particular solution. P or steady state solution is the same thing. Homogeneous solution, and the particular solution. This is so-called, in the engineering sense, transient solution. This is called the steady-state solution. And general solution is combination of these two solutions together. Then that's a total solution. Very important. And this is like a homogeneous solution. And this is like a particular solution mathematically. But or in engineering sense, this is called the transient solution. And this is called the steady-state solution. You remember all this, right? Or otherwise, just learn from here. Because usually when I do something, I start from the bottom and build up. That's what some problem is when you read some book. You jump right at the middle, then it takes a time to catch it. Then you're spending lots of efforts. But if you introduce a couple of pages for background, baseline information, bang, you can hit very next page all the solution. So this is what I'm really giving you, the very detailed steps. So here is a homogeneous solution and particular solution. And a homogeneous solution is like this for the startup solutions. Or you can call as a free vibration solutions. Startup. When you start the machinery or you start the ship, then the shaft start to roll. Okay, shaft start to roll from 0 to certain RPM. RPM is a revolution per minute. You can convert it into a hertz. Cycle per second, okay? Revolution. So then then engines, you might have such experience as the proportion shaft to start to roll and RPM really goes up. Willis, you should have experience when you have a Singaporean naval ship. And the ship rattles. As it rolls faster and faster, it really rattles, then stabilize. All the rattle disappears and goes, passing by. Why? At the beginning, when it rolls, what happened? Frequency is a sweep there, right? From 0 RPM, it goes and higher, higher. Then it hit the natural frequency. Then they love each other, right? Then they rattle together. Then the rolling RPM is moving faster, right? Then natural frequency calm down. Oh, he's gone. Then calm down. Then when it goes into the operating RPM, everything is all smooth, right? He's gone. That range is like a homogeneous solution. Transient region. But after it getting into particular frequency, it stay there. Okay, 30 knots, we are moving. It's a steady, very steady state. Okay? It giving that particular RPM. That's what the steady state region is. This is a startup region or transient region. This is as a result of the homogeneous solution. So this HP is a solution with a 0. Right hand side is the forcing function, right? Mass times acceleration, right? So 0 situation. if it's a zero situation, free vibration, the solution is sine or cosine function, right? This is all they do, reality. I'm not just telling you to look at the math. In reality, sine, if you start from the zero, then there's a sine function. If you look at, this is a p, then there's a cosine function. Sine cosine function is identical solution. Only difference is phase shift is 90 degrees. That's about it, right? Question is where you start. So general solution is the homogeneous solution is combination of sine and cosine, isn't it? That's what this is. YH is A sine omega nt plus B cosine omega nt. You can get into the detail, but that's a homogeneous solution. So now the Y homogeneous solution Y homogeneous solution T is equal to A. How many constant you have? Unknown constant. A and B, that's unknown. How do you get that? Strategy to solve. By what condition? Initial condition. What does it mean, initial condition? What was the initial condition for ship shock problem? Everything's all calm. I had a hard walk and look outside. It's really beautiful horizons out there. I don't see anything but just horizons. Sit back, relax. And they announced we're going to have a movie tonight in the ward room in the ship. Then everything's calm. What does it mean? Convert into math. Displacement is equal to initial displacement, initial velocity, initial condition, isn't it? They are zero, right? So here, A and B are determined by initial conditions. So I have A, did I use a sine? Okay, sine omega nt plus B cosine omega nt. This omega nt, what's the unit of omega nt? Radian, right? Because omega n is radian per second. Times multiplied by second, right? Second cancels out. Then result is radian. Sine radian, okay? So then that's what that is. It's giving you the position. Sine omega n, radian. 0 to 2 pi. 0 to 360 degree. Tie with always when you learn, even if it's simple matters, connect with reality. Where do you use? So now you can determine A and B, right? But there is a point to be very careful to get the solution. So, well, this is a homogeneous solution with two unknown, which can be solved by applying the initial condition. And second is a particular solution, which is a function of the right hand side here. This is a forcing function. And so I said, okay, I don't know, but let's say some alpha unknown, right? And z double dot. To get the particular solution, which means a steady state solution. So, okay, then I have alpha z double dot, which is proportional to this guy. Then you can determine the y there. then you can plug this guy into the equations of motion. When I say equations of motion is y double dot plus omega n squared, y is equal to minus z double dot. If you plug in, then you can determine the alpha. So when you determine the alpha, it happened to be the minus m over k, which then you can claim that alpha is minus m over k. Then you can determine the particular solution is minus m k z double dot. Now you have to be careful from this point. Well, I think I'm going to do that next class. In the solution, you have to be careful for one couple things. Okay, any questions?